Hello students, this is Dr. Diaz. Welcome back. And today we're stepping into one of the most important ideas in all of science. Everything around us, every object, every material, every living thing is built from tiny particles called atoms. They are incredibly small, but they determine everything about how matter behaves. In this lesson, we are going to explore what atoms are, how we know they exist, and why understand them give us the power to understand the world at a deeper level. So let's begin our journey into the building blocks of matter. Let's start with a simple question here. If you take the graphite from a pencil tip and they keep cutting like into smaller and smaller pieces, how far could you go? Eventually, you will reach a point where you cannot divide it anymore without losing what makes a carbon. The smallest unit is the atom. And the word atom actually comes from the Greek word atomos, that means indivisible. Atoms are fundamental building blocks of all matter, like Legos that you use to construct things. Scientists suspect atoms exist long before they could prove it. One key piece of evidence came from Robert Brown, who noticed that tiny particles exist suspended in water moving constantly. And Einstein could prove mathematically that later. So at the first, no one knew why, and Einstein explained this motion mathematically, and Jean-Pierre confirmed it experimentally. Their work finally convinced the scientific community that matter is made of tiny particles, atoms, that are constantly in motion. Even though atoms are incredibly small, modern technology allows us to image and even manipulate individual atoms. There are about 91 naturally occurring elements, and the scientists have created more in the lab. Each element is defined by its atoms. Atoms are so incredibly small that it takes tens of thousands of them stacked together just to equal the thickness of a single sheet of paper. Long before modern chemistry, philosophers like Leucippus and Democritus proposed that matter was made of tiny particles moving through empty space. But others like Plato, Aristotle, believed that matter was continuous and made of four elements only: fire, air, earth, and water. It wasn't until John Dalton in the 1800s that we had strong scientific evidence supporting the atomic model. To understand how Dalton built this atomic theory, we need three key laws. The law of conservation of mass, which says that matter isn't created or destroyed in a chemical reaction. That means if I start with carbon and hydrogen, even if they combine in a different way, at the final product I will still have carbon and hydrogen. And if I start with 100 grams, I will end up with 100 grams. That is conservation of mass. And then we have the law of definite proportions, which says that a compound always has the same ratio of elements. Let me grab my pen over here. So water will always have 2 hydrogen and 1 oxygen. This is what makes water compound over here. That is the definite proportions. And the law of multiple proportions says when two elements form more than one compound. Imagine if you have a carbon and oxygen, and then they react in different ways, producing carbon monoxide or carbon dioxide. If you do the ratio of both, I know that here in carbon dioxide I have 2 oxygen per 1 carbon, while here I have 1 oxygen per 1 carbon. So the ratio would be 2. So this is the law of multiple proportions. Okay, these laws only make sense if matter is made of discrete particles. So Antonio Lavoisier formulated the law of conservation of mass. And as I said, it states that in chemical reaction, matter is neither created or destroyed. So if I start here with the oxygen and the hydrogen molecules over here, and I have 100 grams, at the end I will produce 100 grams of water. So this is the idea. So this law is consistent with the idea that matter is composed of small indestructible particles. Let's test your understanding over here. When a log completely burns in a campfire, the mass of the ash is much less than the mass of the log. What happens to the matter that composed the log? So the matter that composed the log reacts to form gases that are released in the air. The matter that composed the log is converted in energy, or the matter that composed the log is still present in the ashes but has a much lower mass. Which you want to think? So pause your video and think by yourself. Here in this picture you can see a log burning. So, and then you can see the ashes over here. And you see some fume going up over here. What is that? So, when a log burns, it undergoes a chemical reaction that we call combustion. So we react with the oxygen in the air. So the carbon and the hydrogen and the other elements in the wood react with the oxygen in the air to form gases like carbon dioxide, water vapor, right? And other trace compounds. These gases escape into the atmosphere, which is why the remaining ashes will weigh much less than the original log. So letter B says the matter that composed the log is converted into energy. That's not quite right. Energy is released during combustion. I could put some energy here, enthalpy over here. So, but the matter itself is not converted into energy, right? That would violate the law of conservation of mass. And here it's because the ashes are still present, right? In the ash. Only a small fraction here, like the log composed, the log is still the matter that composed the log is still present in the ashes, but it has a much lower mass. This, as I said, would violate the law of conservation of mass. Only a small fraction of the original matter remains as ash. Most of it has chemically transformed and dispersed as gas, like CO2, water, right? So the law of definite proportions. I already explained that, but let's use Lego blocks here to explain. So if you build the same Lego houses twice, you always use the same numbers of red and blue blocks. Imagine if I have to produce a house, I needed 2 red blocks, or 4 red blocks over here, and I'm gonna use to construct my okay, it doesn't look like a house, but if I have to reproduce this, I'm gonna use the same quantity of blocks and the same type of block. So then I will produce the same kind of house, the same number of blocks, like we do water molecules. Doesn't matter if your water molecule is in gas or liquid or solid, like ice. I will always have 2 hydrogen and 1 oxygen. So that is the law of definite proportions. If I have to produce CO2, I will always have 1 carbon and 2 oxygen. That is carbon dioxide. It's always in the same proportions. Okay? So that is the law of definite proportions. If I have the decomposition of 18 grams of water, will result in 16 grams of oxygen and 2 grams of hydrogen. Or an oxygen to hydrogen mass ratio. So here is the mass of oxygen, see? This is the mass of hydrogen. So will be 8 per 1. That means I have 8 grams of oxygen per 1 gram of hydrogen in each water molecule. So if I write down like this, you already know that this is not water. This is hydrogen peroxide, completely different from water. So see, this is the law of definite proportions. Let's test your knowledge again. We just saw that the mass ratio of nitrogen to hydrogen and ammonia is 4.7 per 1. If a sample of ammonia contains 10 grams of hydrogen, how many grams of nitrogen does it contain? So press stop in your video and try by yourself. So here we have nitrogen and a hydrogen. So I know that I need 4.7 grams of nitrogen and 1 gram of hydrogen to produce ammonia. So what I'm going to do is, so I have 10, if I have 10 grams of hydrogen, and I know that to produce ammonia, I need 1 gram of hydrogen for 4.7 grams of nitrogen. So we're going to cut here and multiply over here, so it'll be 47 grams of nitrogen. So the answer is D. So the law of multiple proportions, as I said, can be expressed as a ratio of small whole numbers. What is the law of multiple proportions? When two elements, like let's call them A and B, form two different compounds, the mass of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. How that works? Imagine the blocks again, right? So if I have 2 reds, I could use, like, to construct my house, remember, to construct my house, I could use 2 red blocks and 1 blue block. But I could also use 1 red block and the 2 blue blocks, and I will still construct a house, but it will be a different house, like carbon plus oxygen. So I can produce carbon monoxide and carbon dioxide. So they will combine in different ways. One carbon combined just with 1 oxygen, while the other carbon combined with 2 oxygen, forming different compounds. That is the law of multiple proportions. Let's look to this example over here. Carbon monoxide and carbon dioxide, which are 2 compounds composed of the same 2 elements, carbon and oxygen, and these are the examples that I'm giving to you since at the beginning. So the mass ratio of the oxygen to carbon and carbon dioxide is 2.67 per 1, right? So therefore, 2.67 of oxygen reacts with 1 gram of carbon. While in carbon monoxide, however, the mass ratio of oxygen is 1.33 per 1, or 1.33 grams of oxygen to every 1 gram of carbon. And I can produce the ratio over here, right? So the ratio of the 2 masses is itself a small whole number. If I have the here mass of oxygen to 1 gram of carbon in the carbon dioxide, when I know that it's 2.67, while in the carbon monoxide, 1.33. So if you divide those 2, I'm gonna have 2. So here the carbon dioxide has a central carbon atom, right? So we have the here with the oxygens over here, and here we have 1 oxygen. So to prove the law of multiple proportions, you only need to divide those numbers, right? The mass of oxygen per carbon over here, and you're gonna have a whole numbers. Okay. So let's look to the Dalton atomic theory over here. So this atomic theory explains the laws, the three laws, as follows. Each element is composed of tiny indestructible particles called atoms. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Atoms combine in a simple whole number ratio to form compounds. Remember, like water, A2O. Atoms of one element cannot change in the atoms of another element. A chemical reaction atom only change the way that they are bound together with other atoms. Remember, carbon and oxygen, we can produce carbon monoxide, we can produce carbon dioxide. So they bound with different quantity of oxygen, but they still carbon and oxygen. So let's try test your understanding over here. Again, press stop in your video and try by yourself. Which statement best capture one of the differences between the law of definite proportions and the law of multiple proportions? So the law of definite proportions applies to two or more samples of the same compound, while the law of multiple proportions applies to two different compounds containing the same two elements. Okay, the second is the law of definite proportions applies to two different compounds containing the same two elements, while the law of multiple proportions applies to two or more samples of the same compound. None of the both laws apply to multiple samples of the same compound. So the answer is the first one. And it's right. Remember the Legos? So the definite proportions applies to two or more samples of the same compound. So I can have a different quantity of water here, so 200 grams of water. So I will always gonna have 2 hydrogen per 1 oxygen. 2 hydrogen per 1 oxygen. Doesn't matter the quantity I have over here. If you have a liter of water or 100 milliliters of water, water will be always in these proportions, H2O. So, and the law of multiple proportion applies to two different compounds containing the same two elements. Remember, CO2 and CO. So we can make a ratio. Oh, sorry, I put a CO2 again. So CO and CO2. So, but the ratio will be always the same, 2, right? So in the first one, I have 2 oxygen per 1 carbon, and here I have 1 oxygen per 1 carbon. That is the multiple proportions, because we have 2 different compounds containing the same 2 elements. And that's it. That's all. Bye for now. This is the part 1 of this chapter. Bye.